In this lesson, we're going to examine the graphs of exponential functions, how we can make them, what they usually look like, and how we can solve things from them. So it really is just a series of examples today. We're going to just get some familiarity with these new ideas. So the population of fleas in a dog after t days is modeled by this equation right here. I want to fill in some values in my table. So when t is 0, how many fleas do we have? Well, we end up with 4 times 2 to the 0 over 4. In other words, 4 times 2 to the 0. Anything to the power of 0 always equals 1. So 4 times 1 is 4 fleas to start. As we work our way through the next ones, the only thing that's going to change is our exponent. I'm just going to change exponent here. Okay. So if it's t 4 days, we get 4 over 4, which is 1. 2 to the power of 1 is 2. 4 times 2 makes 8. If we try 8 this time, we're going to get 8 over 4 is our exponent. So now it's 2 squared. 2 times 2 makes 4. And 4 times 4 is 16. And hopefully you notice there's a pattern going on in our table here. We'll try the next one. What's going to happen this time? 12 over 4, power of 3. 2 to the 3 makes 8. 4 times 8 makes 32. If you notice, the n values keep doubling. So we can probably fill in the next ones pretty quickly. 64 and then 128. And it's true because our pattern in the x's is going up by the same amount each time, going up by 4. If they weren't going up by the same amount each time, then we'd have to worry about our table more. But because we're following a pattern in the x's, we know there's going to be a pattern in the y's. I want to graph this now. So we're going to take some graph paper. I put some on the website, so if you're working off the website, it might be good graph paper to print off so you can use this. I can probably fit more than one graph on each thing. We want to graph 0 to n, or sorry, 0 to 20 for n. N is our x-axis down here, okay? And 0 to 20. To make it life easier, I'm going to pick, go up by a value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Only 16 across, so I'm going to go by 2's. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's our days. Fleas up the side. We started at 4, we went all the way to 128, so it grew pretty quickly. So I'm going to go by 10s for this. So 10, 20, 30, 40, 50, 60, 80, 90, 100, 110, 120, at the very top here, 130. And we want to graph this. So after 0 days, we had 4 fleas. That'll be right there. By the time we got to 4 days, we're up to 8 fleas. And the nice thing with this grid paper, all the extra lines, you can get them pretty exact. 8 days, we're up to 16 fleas. 12 days, we're up to 32. 16 days was 64. And 20 days, we're up to 128, which is way up at the top here. 128. And we join them together, we should make a nice smooth curve. And it's going like that. Okay. This general shape is an exponential shape, something that grows, but it's growing at a faster and faster rate. It's getting steeper and steeper as you move to the right. We call this an exponential curve. Part C. Using our graph, estimate the number of days it would take for the population to reach 55 fleas. So 55 fleas would be right about here. And since I drew my graph pretty accurately, I can go down and say, I think it would take approximately 15's in the middle of that, so 15 and a half days. That's for part C. So, and I'd be okay with a number you chose there, maybe approximately 15.5 or 15.6. It's an approximation. And that's all we can do is approximate from the graph. We know 16 days is 64, so it's going to be slightly less than that, right? Okay, where do these equations come from? Well, an exponential function, any equation, has the exponent as your unknown value. Right? You're always going to have some sort of base. In the last one, our base was actually 2, so 2 to the power of x. There's more going on than that, but the base was actually 2. Anytime you have a base that's greater than 1, we call that an increasing function. It's going to go up to the right. okay, like the one we just did with the fleas. Anything that's less than 1 but greater than 0, so for example, we had 1/2, it's a fraction, less than 1, okay, are going to be decreasing functions. Okay, they're going to start high and then they're going to go down to the right. You cannot have a base that's a negative. Okay, if you had thought you have an exponential function that looks like -2 to the x, the problem with this is if you made a table and you tried, let's try nice numbers here, we get 2 to the -2 to the 0, which is 1, and then we get -2. -2 squared is 4, and then we get -8, and then we get +16. And if you try graphing that, you'd be here, and then here, and then here, and then here, and then here, and then, right? And those things would not be connected to each other. They'd be disjoint from each other. That is not an exponential curve. Our curves have to be smooth functions. And one choice or two choices, increasing or decreasing. So we're going to take a look at another one. The population of rabbits on the farm is given by this equation. I want to know the original population. My original population comes from what happens at the beginning. If n is the number of weeks, and I want no weeks to go by to be at the beginning, I say n is 0, my population of rabbits will be 50 times 1.07 to the 0. That's my initial value. In other words, there's 50 rabbits. Okay, well, how many rabbits were present after 15 weeks? Well, n is 5 weeks, right? So n is 15. What do we get for rabbits? I'll get 50 times 1.07 to the 15. You can use the calculator for this stuff. And I got 138 rabbits. It also wants us to figure out 30 weeks. So if n is 30, same equation. We're just going to change our exponent to 30 this time, and up to 381. So like the previous question, it's going to start slowly, and then it's going to start building faster and faster and faster. You want to sketch the graph again. So use the same graph here. I'm just going to erase this one, make a new one. Okay, so this time my x-axis is my rabbits, my weeks. And my y-axis is my rabbits. And what are we going to choose this time? Let's go by, let's go by 5s. So 5, 10, 15, 20, 25, 30. I know I want to pick numbers that I know would make this work a little bit. I already saw that I had 30 weeks as one of my questions. Rabbits, we have to reach a population of 381 after 30 weeks, so let's go by 50s. It doesn't really make a difference what your scale, as long as you can fit all the information on, right? 381 is a number I know, so I want to go a little bit higher than that, so let's go to 450 for now. What do we know? We know at 0 weeks there were 50 rabbits, so I can make that dot for sure. I also know that at 15 weeks we're up to 138. 15 and 138. We're going to have to estimate a little bit, that's okay. The lines are going by tens, right? So 138 would be slightly below 140. And at 30 weeks, we're up to 381. So 360, 370, 381, right about there. And that's probably enough information to be able to make my curve. I know it's going to do this. There's my graph. The next question asks, how long would it take to reach 500? So we need to extrapolate a little bit. I need to go beyond the range of my graph. So 500 is up here. I go across, I go down, and I can say it's going to take me approximately 34 weeks. Okay. Some things to point out with this graph again. Notice that our base, that's our base right there, it's bigger than 1, which means it's growth. That's why I went up to the right. Not all our bases are going to be whole numbers. Decimals are actually very common when we deal with exponential functions. Okay, we'll try the next one. When a liquid in a container is placed in a refrigerator, its temperature is given by this equation. Okay, find the initial temperature of the liquid. So when no time has gone by, when T is 0, what is our temperature? We get 100 times 0.933 to the power of 0 or just 100. I hope you've noticed by now that the number out front is usually your initial value. The part inside is how things are changing. Okay, let's figure what's happening after 10 minutes. So t is time in minutes, so t is 10. Our temperature is 100 times 0.933 to the 10. And we are now at a temperature of 49.98 degrees Celsius. This was 100 degrees Celsius. After 30 minutes, so T is 30, our temperature is 100.933 to the 30 this time. I hope you notice our temperatures are dropping. We're down to 12.49 degrees Celsius. Okay, why is it dropping? Well, if you look at your base, you see a number that's less than 1. So that's a decreasing function. Okay, we want to draw the graph of this function again. We can do that. Okay, back to my graph. Get rid of that one. Okay, we got time on the bottom this time. And we went up to 30 minutes, so let's go by 5s again. 5, 10, 15, 20, 25, 30, 35, 40. Always good to go a little bit past. Our temperature was up the side. It started at 100, so we have to get up to 100. So let's go by 10. It's 10, 20, 30, 40. And what do we know? We know it was at 100 degrees to start. We know after 10 minutes, at 10 minutes we were down to basically 50, and at 30 minutes we're down to 12 and a half. So 50 and 12 and a half. 50 after 10 minutes, and 12 and a half after 30 minutes. And we can graph this. It's going to come down this time. Okay. Now, our functions never get into the negatives. They should stay positives. They're going to get smaller and smaller and smaller, but it won't actually hit 0. Okay. Part D, we want to estimate the number of minutes taken to reach 40 degrees Celsius and 10 degrees Celsius. So where's 40 degrees Celsius? We can estimate that pretty easily. It's right there. So I'd say about 14 minutes. So D, 14 minutes to 40 degrees Celsius. And the trickier one, 10 degrees Celsius, that's across and down. Now I say it's trickier because it really kind of depends on how smooth you made your curve. My curve actually looks a little straight in the middle there. If I'd curved it more, it would give me probably a better estimate of how long it takes to get to that 10 degrees Celsius. I'm going to guesstimate about 33 minutes. But according to yours, your graph might be a little bit different than mine. You might be a little bit higher, a little bit lower than that. I know it's got to be more than 30. That's all I know. How much more? It's going to depend on how smooth your curve is. Okay, last one. A refrigerator has an internal temperature of 27 degrees Celsius before being turned on. The temperature reaches 6 degrees Celsius 3 hours after we turned it on. It's known that its temperature is given by this equation, where A and B are constants, they're numbers, and time is measured in hours. And I want to figure out two equations that contain an A and a B. So what kind of information have they given us? They've told us when they first turn it on, it's 27 degrees Celsius. Well, that's a point, right? This is my time. This is my temperature. I can use those with my equation to make a function. So if I take those and I put them into the equation, we're going to end up with temperature being 27. I don't know what A is. I see a 1/2 there, so 1/2 to the time T. T is 0 minutes. I don't know B. I can simplify this equation. What's 1/2 to the power of 0? That's just 1. Or in other words, I can make an equation that A plus B has to be 27. And by taking information that I was given. I was given a second piece of information. I was told that it reaches 6 degrees Celsius 3 hours after being turned on. Well, that's a second point. Okay, 3 hours gets me to 6 degrees. I can do the same thing, put 6 in for my temperature, 1/2 to the 3 plus b. What did we do last time? We simplified. 1/2 to the 3 is 1/8, or if you want to change it to a decimal, 0.125. So in other words, 1.25a plus b. There's some equations involving a and b, and they're really easy to figure out by plugging in information that I know. We should always do that when we have equations. Okay, part B, solve for these values now. So I've got 2 equations and 2 variables. Okay, there are options you can do here. I'm going to use the idea of elimination, where I take my 2 equations, one there and one over here, and then I can subtract them. 27 minus 6, that gives me 21. A, which is like 1a minus 1.25 is negative 0.25. A and b minus b is gone. If I solve this for a, I get negative 84. Sorry, mistake there. That didn't make any sense. I actually made a mistake back up here when I was writing down my 0.125. I changed it. You may have noticed. So this should be 0.125a. Fix. Sorry, guys. Yeah, this should be 0.125a. I knew it was the wrong answer because when you subtract, you should end up with a negative. We talked about that, right? Okay, so I want to solve for a. So 21 divided by 0.875a, a comes out to, I believe it's 24. Okay. I also know that 27 is a plus b, and if a is 24, well, doesn't that mean b has to be 3? So now I have myself an equation. The temperature at a given time is made up of 24, that's your a value, times 1/2 to the t plus b. Okay? And then part C, figure the temperature after 5 hours. So I can do that. Now I have my equation. My temperature after 5 hours will be given by 24 times 1/2 to the 5 plus 3. And since we already know that 3 hours is down to 6 degrees, we should be able to judge the accuracy of our answer, 3.75, to be somewhat reasonable. And it's starting to level off. It started up high and it went down, right? Because we have a fraction as our base. Okay, that's it for today. The homework is a handout. We just want to get used to drawing these things, what they look like. The idea of a whole number base or bigger than one base goes up to the right. Less than one decreases, decays, goes down to the right. And trying to start recognizing some of our initial values, things like that.